Hello everyone, today I'm just going to be taking you through my machine learning 2 final project, which was basically on the analysis of distribution-based clustering methods. Essentially what this project was supposed to do was to give us a better idea of how different clustering algorithms work and what essentially their parameters do to the results that you get as well. So first and foremost, we basically had to pick out 10 different data sets. I used the UCI website for each of these. So this is a mix of different types of data sets. Some of them are just purely clustering and some of them are clustering with classification as well. We got the Facebook live sellers in Thailand, which is essentially a data set of different Facebook ads that have been posted in Thailand for selling different things. Turkey student evaluation data set is a faculty evaluation form. Wholesale customer data is about people's spending patterns. Colon usage is basically DNA genetics and what all is there in that DNA. So chemical composition of ceramic is basically, as the data set suggests, it's ceramics and basically what chemical composition is there in such substances. Absenteeism at work was an interesting data set wherein you got information about different people who took any sorts of leaves from their work, and essentially you got insights of what sort of person they are, how old they are, what workload they have, how far they live, all of that. It was a very interesting data set. HCV was another one, which was about blood tests and essentially telling us about different blood types and their records. HTRU2 and parking in Birmingham were very large data sets. So essentially during the entire process, I only used the first 5,000 records for both of these. And the shill bidding data set was an eBay auction data set. I essentially started my entire project off by importing all the libraries that we're going to be needing later on. Initially, just for my own convenience, I initialized a list called datasets. It was empty. I appended all the single files that I had in the datasets folder. And this was the list that I got at the end of it. And I assigned a different value to all these different data frames. DF1 through DF10 has this now. So essentially, I began by pre-processing all my data sets. So the essential rule was to only use columns which were numericals. And if they were not numerical, if they were textual columns, then make sure that they are classifiable, and then I would label encode them as well. So for example, for DF1, you could see that status ID is not needed. Columns 1 through 4 are not needed since they're all NANs. Status published is not needed because that's just a timestamp. Status type was video, photos, etc. But the thing is that this had a limited number of values that could occur. So I ended up label encoding that. And another thing that I did across the board with all the data sets was that I used min-max scaler to scale the data to a range between 0 and 1. Moving on, I did the similar thing for data frame 2. Considering they were all numerics already, I simply applied min-max scaler to get this. Data frame 3, similar again. This was the original data set, just applied min-max scaler, got that. In DF4, triple U and WC seem like they're completely numerical, but in the middle there were a few textual rows in there as well. So I ended up just deleting these two columns to make it easier. Species name was also deleted because there weren't enough. There were too many of these, right? So where you can see there are 13,016 different species names, even though there are only 30,028 different rows. So there was no point of this, and I deleted this entire column. Kingdom, however, there were only 11 unique IDs over there, so I just ended up label encoding this. Moving on, I did the same thing, min-max scaler, converted the entire range. DF5, similar, 88 rows, 19 columns. I checked the number of unique ceramic names. There were 88 of them, so essentially it was like an ID, and I just ended up deleting that because there was no use. Then there was the length of parts, right? So basically, part was this column which either had body or a glaze on it. So I just ended up label encoding that and passing this entire thing through the min-max scaler again. Similarly, for all of these different data sets with data set 8 having the first 5001 records, same thing with data set 9 having the first 5001 records. Anyway, so after this was done for my own convenience, I initialized a list of lists, which was called datasets XY. In this, each item in the list is a list in itself containing the X and the Y variables. So wherever there is no Y variable, I just made it mention none. Otherwise, I mentioned the Y variable. This is easier for later recovery of these uh, items. Anyway, so moving on, the first thing that we were supposed to do was essentially figure out what different hyperparameters do to the Gaussian mixture model. So I ended up building a grid search cross validation function, which used Gaussian mixture as the estimator, and the parameters that it was going to try out were going to be the n components from 1 through 7, the covariance types from full, tied, diagonal, and spherical, maximum iterations from 50 to 150 at increments of 25 and then 250, and initialization parameters, which were k-means, k-means plus plus, random, and random from data. Essentially, what this part is doing over here is that it's trying all these different combinations. So 7 multiplied by 4 multiplied by 6 multiplied by 4. And that's going to be the number of different combinations that it's going to try and give us results for each of them. So CLF was essentially going to be what was returned, and that's the name that I also assigned this variable, which was going to pass my df5's x and y through this function in order to get a result. So over here, this is an entire function that I've written down to essentially split the information that you get over here to different parameters and then just have them all put into one table. This is just the head, so this is just the first 5 columns over here, but the full thing you can see over here. Over here, what I've done is that I've actually taken the information that we had over here, grouped it by a simple either covariance type, initialization parameter, maximum iteration, or n components. So essentially what it does is that it takes the unique counts for each of these. So for covariance type, it would take your full, it would take essentially all of these, right? So you have your full, tied, diagonal, and spherical. So it would take those and then calculate the mean of all of these other things such as time, score, etc., etc., and present it over here. I concatenated all of these, so I grouped it across covariance types, initialization parameters, maximum iterations, and then components, and then ended up concatenating all of those along the records and presented it in a single data frame over here. This data frame was later exported for easier use. I'll come to that later. So using this table, I was able to identify different patterns, right? So over here you can see is that I have highlighted the first four rows, which are basically different covariance types. I looked across the different values over here um, in order to figure out which parameter had the highest average, let's say, rank score over here, which in this case seems to be full. Even though full is the second slowest model over here, but it gives you a good accuracy. In case you want to drop down a little bit, you can go to spherical, which gives you the second best accuracy, while also being the much faster. Later on, you can also check different initialization parameters as well with k-means through random data, and you can check all of the scores and time taken over here and make your analysis. So this is the analysis that I've done considering all of these scores. Then later on, essentially, we came up to figure out how the GMM models would compare to other clustering algorithms. One thing that I figured over here was that the number of iterations, maximum iterations, did not make a difference, or at least it had no correlation between an increase in the number of iterations and an increase or decrease in score, or vice versa. So, given that the unpredictability over here, I figured that that's not something that I want to be optimizing while going forward. So over here, I've basically defined a lot of different functions. The first one being the GM best estimator. This is going to take the Gaussian mixture, test it across these three hyperparameters and figure out what the best model is for each data set that I'm going to pass through it. So I initialized an empty dictionary, passed through different x's and y's using the datasets xy list of lists that I made earlier on, and it gave me the best estimators for each of them. So for data frame 1, you can see that the best estimator is the initialization parameter random and then component 7, whereas for data frame 5, it's covariance type diagonal, initialization parameters as k-means plus plus, and then components as 2. Moving on, I also made a lot of different pipeline formulas for myself. This is the most important one called score, which essentially takes in your algorithm name, the number of clusters, the x-axis, which is basically your features that you're going to use to predict or cluster different things together, prediction labels, which is basically your clustering algorithm's output, and your y, which is your target variable if it exists. It initializes to none because not all problems are ones with the target variable. Moving on, over here you can see that I've done a bit of error handling over here. So in case the prediction labels, which is over here, the output of your clustering algorithm equals to 1, as in it did not cluster anything into multiple clusters and just put all the data points into a single one. In case that happens, I'll just give a silhouette score of 1, as again, there is no overlap, there is no wrongly classifying any single data point. So I believe this silhouette score should be 1, even though it is a very badly performing algorithm over here. So basically, I just did this for error handling. The actual score is being calculated over here, which is silhouette coefficient. We're gonna take the silhouette score function, pass the x label and the predicted y labels over to it as well. And in case we do have a target variable, so in case y is not none, it's also going to calculate the homogeneity, completeness, VM score, adjusted R score, your mutual information, and the folk score, and then add them all to this data frame called metrics that we had initialized over here. It's going to add all the scores over there and then return the metrics table. It's also going to show us different plots using TSNE. TSNE is essentially TSNE is this method of mapping your entire data set onto two separate axes, and you can essentially get a good idea of what the distribution of the data sets using that as well. So it uses that to generate different graphs and display them as, and you'll see that as we go along. Now I basically decided to also code a lot of different functions for each different clustering algorithm that I'm going to be using. Each of them is going to be taking in two inputs, x and y being again defaulting to none in case it's not a classification problem. The reason that I defined a different function for all of these was also because I wanted to get the best possible hyperparameters for each of these. So in each of these, k-means, agglomerative, dp scan, optics, spectral, affinity propagation, and GMM clustering, etc., you would see that we have different parameters that are being tuned. So for example, for affinity propagation, you have the different damping values over here, 0.5, 0.7, or 0.8. It's going to apply affinity propagation across on the data set 3 times, calculating the silhouette score, and then checking which of these values gave you the highest silhouette score, and then calling that for your final pass through, right? So over here you'd see that at the end of the day you will just return your score function, which was what we had defined earlier on, and pass the algorithm name, which is over here, affinity propagation, number of clusters, which is over here, the x, which is basically all your features, essentially your data, and the model, which is your model that has been trained over here. In this case, it's affinity propagation, yeah, and so on and so forth. Same thing has been done across all of these different clustering algorithms. At the end of it, we have one simple function which we're going to be passing all the data frames through. It's called dataset performance. Essentially, it takes in again x and y, and it passes them through all of the different clustering algorithms that we have defined above. And then at the end of it, it just takes all of the scores that you get in return, and then it concatenates them into one simple data frame. So it's easier for you to essentially check different clustering algorithms' performances across each different data frame. Now over here you can see is essentially just I have applied the entire function that I defined. So you have dataset performances. I've passed TF1X through it. You can see it's working over here. This is the TSNE in action. So you can see the entire dataset has been mapped onto a 2D plane. And you can see Minibatch has performed decently well over here. It's managed to capture the different clusters properly. Agglomerative has also performed decent, but not entirely the best. DBScan has just taken the entire data frame into one or two different clusters. I wouldn't even call the second thing a cluster. I think it's just more of a noise point at this point. But yeah, that's what DBScan has done over here. It hasn't really performed well. Similar thing with optics clustering and spectral clustering. Affinity propagation is also here, but it has defined 60 different clusters, which is also not good. So you can see at the end, the table is over here. These values are coming out to NANs because this did not have a target variable. If there's any data set with a target variable, all of these scores would also get filled up, and you can compare using those two. You get the number of clusters across each algorithm that you've used from mini batch agglomerative, DB-scan, optics, spectral affinity, and Gaussian. And you also get their corresponding silhouette scores and DB scores over here. df2 was one where we did have a target variable called df2y, so I've passed that, and over here you can see the performances across different algorithms as well. At the end of it, you get this table over here, which is showing you exactly what the scores were, clusters, again, same thing. So I can take you through all of these data sets, which is essentially the same again and again. I've gotten the tables at the end of it, right? But in order more for us to have better convenience on this matter, I've also exported all of these to different Excel files and then concatenated them as well. So if I come over here, you can see that this file has the scores across all of them. So from DB1 score, DB2 score, DB3, 4, 5, all the way till 10. It also has the GM all variance scores, which was the Gaussian mixture hyperparameter tuning that we tried to do. So it showed us the entire table over here. The comparison one is when we grouped them by separate by using the several covariance types, initialization parameter types, maximum iterations, or the number of components, and the average values that each of them got across the different metrics over here. But the most important one sheet over here is called all scores, which essentially had all of these DF1 through 10 summarized over here into one giant table. And this table essentially could be used to group or view the data however you want to, right? So if you just want to view a specific algorithm, let's say optics clustering, you go over here, you click on optics clustering, and it shows you its performance across all the data frames over here. Alternatively, if you just want to group it by data frame, you can just come here and select, let's say, the sixth data frame and check its performance with all the clustering algorithms that we've used. Lastly, over here, we have this data frame. Essentially, what I did was that I grouped it across different data frames, and then I checked what the best performing algorithms were and the worst performing algorithms were. I noted them down, made a count of how many times each appeared in the top two or the bottom two, and then put them over here. So essentially what I did was that I just took the count of how many times each of these algorithms appeared in either the top two best performing ones or the worst two performing ones. And that's how I managed to come out with what my top two clustering algorithms were, which in this case were mini batch k-means and spectral clustering, and the worst two performing ones, which were DB-scan or optic clustering. Now, this does not mean that DB-scan and optics are always the worst ones. This could very well be the case of the hyperparameters not being tuned properly, considering the fact that both of these usually more often than not ended up clustering the entire data set into one single cluster, which is not how these usually perform. But given that that's happened, given the data that's at hand, these two were the worst performing ones. But again, as I said, that's not a rule that's set in stone. That could just work out well later on as well. Um, that's about it, though. That's basically the entire project. I have also uploaded an article on Medium, which is describing everything that we've done over here. And it's also given a better insight and more analysis on each of these results that we've gotten as well. I'll possibly just link it in the description of this video too. Thank you.